Hello. Here we will take a look at ManiVault, a visual analytics framework by Thomas Kroes, Julian Thijssen, me, Alexander Vieth, and others from the TU Delft, LUMC Leiden, and TU Eindhoven in the Netherlands. ManiVault is a framework for exploration, analysis, and rapid prototyping targeted at high-dimensional data. Right now, we are already looking at some use cases of the system. In the next couple of minutes, we'll discuss our design motivations for the framework and highlight how they led to specific software architecture choices. Analytics software in many domains that is targeted at high-dimensional data utilizes similar sets of analytical and visual tools, for example, parallel coordinate plots, scatter plots, or dimensionality reduction and clustering algorithms. Often, these generic tools are combined with domain-specific ones into standalone applications. But it is unnecessarily time-consuming to reinvent the wheel by re-implementing, for example, a linked selection mechanism for multiple coordinated views every time a domain-specific visual analytics solution is needed. Let's begin with our target audiences. Now, I already established that ManiVault is a visual analytics framework that focuses on high-dimensional data. But even more elementary than that are the questions: who are the intended users? Which problems should the framework solve? And ultimately, how does this shape its design? For that, we built on experiences made during multiple collaborations with practitioners in various fields like systems biology, cultural heritage, and more general visual analytics-focused projects. Besides the practitioners, the software developers of analysis frameworks are integral users themselves, be it from a different perspective. And further, we identified a third group, the application designer. Each user archetype comes with a set of different goals. The developer wants to implement visualizations, algorithms, interaction mechanisms, and more. The practitioner cares about the analysis and exploration of their data and may want to share their results. And finally, an application designer wants to use the framework as a visual analytics design environment to create user interfaces aimed at specific workflows. Of course, most users do not fall exclusively into one of these categories. There's a substantial overlap. For example, a visualization researcher might both implement a novel charts type and subsequently use it to explore results of their own study. A domain expert might first analyze their data in a flexible setup, and once converged to a stable workflow, fix the user interface and share reproducible results in a standalone application. We want ManiVault to facilitate the rapid construction of visual analytics applications for developers, practitioners, and application designers. This means that ManiVault has to be easily extensible with new functionalities. The system must enable flexible workflows in multiple application domains. It should allow for linking datasets and share parameters across visualizations and algorithms. The user interface should be configurable during runtime. A user should be able to save and share the configured interface, including loaded datasets and analysis results. And of course, the entire system should be performant when handling large data. We found that while there do exist many open source visual analysis tools, none fits our need for a framework that's focused on high-dimensional data, is easily extendable, is designed with progressive visual analytics in mind, and allows for flexible visual analytics or system authoring. So, how do we approach this with ManiVault? The framework is implemented as a modular system and consists of a core and plugins. The core application is a lightweight set of managers, while self-contained plugins supply all user-facing functionalities. This modularity provides a means to extend the framework with new functions, but seemingly stands in the way of another requirement that we just mentioned. How can parameters be shared across plugins that are all self-contained? For that, let's have a look at ManiVault's architecture in a bit more detail. The core consists of a set of managers, actions, and some utilities. The managers take care of, for example, the application layout, or plugins. We define 6 distinct plugin types that bundle various kinds of functionalities. Data plugins define, well, data types, like high-dimensional points or images. Each plugin might either consume data that are managed by the core, produce them, or both. A data manager provides the API for passing data and views on data to the plugins. An analysis plugin, for example, might then perform computations on the data and create derived datasets like a low-dimensional embedding, for example. View plugins, meanwhile, provide visualizations and user interactions. They can be based on diverse backends, like OpenGL or D3. Plugins are notified about data changes via the core. If, for example, a user selects a cluster in a scatterplot, the respective viewer plugin can send this information to the core, which will notify all other plugins about this change. For more general parameter sharing between plugins, we introduce special GUI management objects called actions that are linkable during runtime. ManiVault provides a set of common action building blocks like numerical sliders, color maps, and selection modalities. Using the Action API, any custom parameter might be shared between plugins too. Let's delve into this a bit more. Here we see an abstract representation of a common setup. We have a view and an analysis open, for example a density plot and a mean shift clustering. Both plugins use a GUI element of the same type, a decimal action. The density plot to adjust its view, and the clustering algorithm to steer its computation. Each plugin might come with a diverse set of other actions, but we can only link two actions of the same type. To do this, the user first publishes an action, which creates a shared parameter that is managed by ManiVault's core, alongside all other actions that might have been shared before. A second action can then be connected to the published one. Any change to the parameter in one plugin will be synchronized with the other. Here, for example, we make use of this connection to visually find a suitable density estimation while updating the clustering automatically. At this point, we should revisit one of the application examples from the intro. We are looking at an analytics setup for a high-dimensional image, just as a domain expert in the field of cultural heritage might do. A viewer plugin displays a false coloring image based on 3 of its 200 data channels. We'd now like to steer the selection of which channels are used for this recoloring. We start with opening a TSNE analysis through a context menu on our dataset, which will open the respective analysis plugin. Here, we can adjust settings and then inspect the resulting embedding in a scatterplot viewer plugin. Next, we define clusters that could be of interest and display their average spectra in a line chart plugin. Now, we'll make the parameter that we want to connect available through a plugin-specific settings window. Here, we could also turn entire GUI elements invisible if we want to share the setup once it is in a well-adjusted state. Alternatively, we might switch into a global studio mode, which enables all user interface modifications. When selecting the parameter which we want to share, all parameters of the same time are highlighted. These we can link with. In the next step, we could save this setup as a project and send it to a colleague. Upon opening it again, the setup, including data, open plugins, and parameter connections, will be restored. We just saw an exemplary practitioner workflow. Next, let's have a look at a model workflow of an application designer. To this end, we'll re-implement a SiteExplore viewer application in ManiVault. This is an application used for the exploration and comparison of cell types between animal species based on thousands of gene expressions. Our goal here is to share a standalone application that lets others interactively explore the results of a study. We want to arrange and connect existing plugins to create this viewer. As you can see, we already started off with loading our data in ManiVault and computed statistics that we display in a table view. Our data contain embeddings of gene expressions of 3 animal species and several clusters. First, we want to connect the visual properties of these scatterplots which depict the embeddings. In a second step, we want to connect the color coding used in the scatter plots to the data statistics. That is, upon selecting a data dimension, each embedded data point should be colored according to a derived feature of that dimension. Finally, we might want to provide easy access to all relevant parameters of this application in a single panel, just as the original application, which we re-implement here, does. Using ManiVault's action system, we can implement such a plugin in but a few lines of code. Before publishing this project, we could decide to hide all plugin parameters which we do not want to be explicitly exposed. We currently have implemented a range of plugins, including different types of data, several viewers, and common analytics methods. Additionally, there are example plugins that show the setup code for each plugin type. At this point already, development versions of ManiVault have been used in several projects across 4 universities. Thanks for your attention. ManiVault is open source and available on GitHub. Feel free to try it out.